All right, hello everybody. Today we'll be presenting an analysis of systems challenges to building reliable, accurate, and robust visual SLAM systems in the face of changing environmental conditions and varying resource-constrained hardware. Visual SLAM systems are used by applications such as mobile augmented reality, autonomous driving, and service robotics. These applications require building a 3D map of an environment as a robot traverses through that environment. SLAM systems help build that map by simultaneously localizing the robot as it traverses through the environment and building a map. For visual SLAM systems, this map is built using visual sensor data, so RGBD, monocular, or stereo camera frames. There's been a significant amount of previous research on SLAM systems, and the majority of that research has focused on the algorithms side of it. And as such, the current state-of-the-art SLAM systems are quite algorithmically mature. However, their system design has remained largely unchanged over the years. So why do we care about the systems design? First, SLAM systems and the applications that use them have strict performance requirements. Second, SLAM systems are typically deployed on various resource-constrained hardware. And lastly, they are affected by real-time dynamic environmental conditions. In our experiments, we've seen that SLAM systems suffer from subpar performance due to poor systems design. We've identified 3 interconnected systems challenges that are the major bottleneck for building reliable and robust SLAM systems. These are timeliness, concurrency, and context awareness. And in this presentation, I'll be going over those 3 challenges. In our experiments, we've focused on analyzing OrbSLAM2, which is a SLAM system that comprises of 3 modules. While not all SLAM systems are exactly the same, most SLAM systems follow a similar system diagram or system implementation. The specific algorithms within each of the modules might change, but for the most part, the modules themselves stay the same. And there are similar newer systems that follow the same organization as OrbSLAM. Those are Chimera and OpenVINS. So when we talk about SLAM, what does it actually look like? What does this map look like? So on the bottom, we see a video stream from a car going through a city street. And on the right-hand side, we see the map that OrbSLAM will build. The map is comprised of 2 main core components. The first one is a keyframe. This is an image taken at a pose. So that pose is a location and orientation. On the right, those keyframes are the blue triangles. And then the second core component is a map point, which is a feature seen inside of a keyframe. And this feature likewise also has a pose. So on the bottom, those features are the green squares, and on the right-hand side, they're incorporated into the map as map points as those red dots. And all of the modules inside of the SLAM system are accessing this global data structure and optimizing this global data structure. So in our experiments, we've run our experiments on 2 different devices with 2 different frame rates. The first device is a Jetson TX2, which is a representative resource-constrained device. And the second device is a laptop, which is closer to a mobile service robot navigating inside of a building. And the 2 frame rates are 10 frames per second, which is the target frame rate for the KITTI dataset. And the second frame rate is 0.5 frames per second, which is used to isolate the individual module performance and minimize concurrency. This isn't a realistic frame rate that would be running at, but it is a good indicator of how the system will perform with ample resources. So now that we've actually seen what the map looks like, we'll go over the first challenge, which is timeliness. So of course, we want SLAM systems to perform as accurately as possible, but we additionally also want them to be as timely as possible. This timeliness is important because the maps that SLAM systems generate are used for other tasks, such as robot navigation or overlaying virtual objects on the real world. And likewise, each of these tasks has their own performance requirements. So if the SLAM map is used by these tasks, it needs to perform as timely as possible to generate accurate and useful results for these extra applications. So the SLAM pipeline is by nature sequential, so the controllable flow from tracking to local mapping to loop closing. But because timeliness is important, this pipeline is actually split into 3 concurrent modules. So the first module is tracking. It accepts a image from the video stream, and it will get a pose for that image based on similar keyframes in the map. It additionally can choose to save that image into the map as a keyframe if that image is novel enough. In the circumstances where it does save that keyframe, that information is passed to the local mapping module. The local mapping module will optimize the map based on that input keyframe. And additionally, the loop closing module will also run on every keyframe and will attempt to detect loops. If it finds a loop, it will align the loop to correct accumulated trajectory drift along the loop. So each of these modules has various timeliness constraints. So the tracking module is actually the fastest module of all three of them. On the resource constrained device, we saw that it takes 103 milliseconds on average for every single input image. However, it has to run very quickly, so it has to run on every single image from the camera. If it doesn't run on every single image from the camera, or it doesn't successfully make keyframes when it should be making keyframes, it has the potential to enter a state called relocalization. This is the circumstance where the SLAM system cannot track the current location of the device, and so it loses its place in the map. This is a separate computationally intensive process where the entire mapping is paused and the whole system devotes all of its resources to finding the place of the device. In the worst scenario, the SLAM system might never be able to recover in the case where, for example, the device moves to a different location and never returns to where the original map is. The local mapping module has a slightly longer duration, but also runs less frequently than the tracking module. So it runs about every 6 to 10 frames on our experiments. And it also has a slightly less importance for meeting its timeliness goals. So if it doesn't keep up with real time, or if it ends up skipping an optimization, we end up with an unoptimized map. This means that there is a higher chance of relocalizations and a result of a slightly worse accuracy, but it is not as critical as the tracking task. And then lastly, the loop closing task has a far longer duration, but also runs far less frequently, and is also more unpredictable in when it runs. It only occurs when there is a loop. But likewise, it also has the most tolerance for longer delays. So the key takeaway here is that SLAM systems have interconnected modules with various interconnected timeliness goals, and future system design should consider that when making scheduling decisions. So onwards to our second challenge, concurrency. SLAM systems consist of concurrent modules that perform computationally heavy operations, and these operations frequently access both read and write to shared data structures. SLAM systems address the shared memory management in 2 key ways. The first is through coarse-grained locks. And we actually found in our experiments that the additional latency added by lock acquisitions was not significant. The second shared memory management technique is through a drop mechanism where for certain resource contentions, one module will drop or minimally process its current task if there is a resource contention with another module. This has a far more significant effect on performance because drops lead to missing map and localization data, which either increases the chance of relocalizations or decreases the accuracy. There are 2 types of drops that we're going to cover. The first one is frame drops, and the second one is keyframe drops. Frame drops occur when multiple frames arrive while tracking is busy. Tracking will only process the latest frame that arrives from the camera. So if multiple frames arrive while tracking is currently processing one, then it'll drop all of the frames in between. On the KITTI dataset, we ran experiments on each of the device and frame rate pairs. And we see that for the most resource-constrained device, which is the Jetson at 10 frames per second, it actually tracks significantly fewer images than the rest of the devices. However, this is because the Jetson enters relocalizations far more often than the other devices. And during this relocalization, no images will be tracked at all. If we actually look at how many images are tracked before any relocalizations occur, which is on the right-hand side, we see that actually the Jetson, the most resource-constrained device, and the laptop track a similar amount of images. So what does this mean? While frame drops can contribute to lower performance, it actually wasn't the reason for the lower performance in our experiments. The local mapping module has an unbounded queue and is a computationally intensive operation. To avoid processing stale data and falling behind real time, the queue length is mitigated through the drop mechanism that we discussed earlier. In the case where tracking attempts to insert a keyframe at the same time that local mapping is working on a map optimization, the system actually chooses to either discard the keyframe or abandon map optimization with a heavy preference for discarding the keyframe. So on the right-hand side, we can see the keyframe creation rate, the rate that I create keyframes for both the Jetson and the laptop. The blue line indicates the rate that I create keyframes, and the orange line indicates the rate that I drop keyframes due to concurrency. So on the top, we see that for the resource-constrained device, the device drops far more keyframes than it creates. And then for the less resource-constrained device on the bottom, the keyframe creation rate and the drop rate is similar. And we can kind of view this gap between these two lines as the degree that resource contention affects keyframe creation. So the key takeaway from this challenge is that poorly designed concurrent accesses contribute to increased keyframe drops, which in turn lead to lowered accuracy and unpredictable results. So onward to our next challenge, which is context awareness. Because SLAM systems process a large amount of that quickly arriving input data, and each of the modules take a long time to, are quite computationally intensive, it is inevitable that there's going to be some degree of overload for some resource-constrained devices. So these devices will have to drop information because there's no way they can ever process the entire workload. Additionally, even when there isn't overload, some resource-constrained devices will always need to drop more data because of the concurrency challenge that we talked about previously. This leads to a high variability in the performance of the SLAM system. So on the right-hand side, we can see the variability in the keyframe creation rate for the Jetson and for the laptop, and that variability is quite high for the Jetson compared to the laptop. And likewise on the bottom, we see the trajectory error that corresponds to the experiments in the graphs to the right. So what does this mean? First, this makes it difficult to rely on SLAM systems when they aren't going to have consistent performance. And it's also difficult to rely on SLAM systems when you can't predict what the performance will be like based on the amount of resources allotted to the application. Ideally, we want the system to gracefully degrade with lowered resources and also have consistent results within a certain device with certain resources. Additionally, for the experiments that we have run on the 0.5 frames per second scenario, we actually see that the modules all take longer to run than they do when we run at 10 frames per second. This makes sense because when I have lower resource contention, I have fewer keyframe drops, and so I have a much larger and much denser map. And likewise, this leads to a larger search and optimization space for all of the modules. And this would be all right, but what we actually see is that the average trajectory error at the end of the run is not significantly better. So for the 0.5 frames per second experiments on the, for example, on the laptop 0.5 frames per second, we see that its average trajectory error is not that much better than a laptop running at the target frame rate. And this indicates that resource-rich devices perform an abundance of tasks that don't significantly increase performance. So a solution to both of these problems is context-aware scheduling. Currently, OrbSLAM2 uses a standard OS scheduler to allocate processing time, but the importance of each task depends on environmental conditions. So previous work shows that some keyframes are more important to overall accuracy than others. And the factors that influence whether a keyframe is important is the number of features that are seen in the image in the keyframe, how fast the device is moving, and whether it's experiencing rotational versus translational movements. So the key takeaway from this challenge is that application context is very influential on the overall function of the system, and we can't treat all concurrent accesses equally. All right, to go over, we've gone over 3 system challenges to building robust, reliable SLAM systems in the face of variable environmental conditions and variable resources. Namely, we have seen that concurrency and context awareness have a significant impact on timeliness, which in turn affects SLAM accuracy. So now I'm going to briefly talk about a couple projects that we're working on that are addressing these problems. The first is Atlas, which offloads a portion of the SLAM pipeline. It offloads both local mapping and loop closing onto an edge device and has multiple clients who are running the tracking task connected to that edge device. And so we actually see in our experiments here that concurrency on the edge device is the scalability bottleneck to the amount of client devices that can connect to the edge device. So here we are looking at alternative ways to either do incremental locking onto or sub-locking parts of the map rather than locking the entire map, or restructuring the map so that concurrency is not as important of a bottleneck. The second problem, or the second system that we are building is Darvis, which is a complete rewrite of a SLAM system that is modular and customizable. So rather than, I have the pipeline and I just run the pipeline as it is, I can plug in different parts of the individual pipeline to create a custom pipeline to experiment with. We're also writing this in Rust, and hopefully that will give us some stronger memory management. And in this project, we are planning on restructuring both the scheduling and the shared memory management completely from the ground up. So that concludes my talk. I'll leave the slide up if anybody has any questions.